Hello, this is Jack Jackson. In this video, we're going to give a very quick overview of differential calculus from Calculus 1. Calculus is an extension of K-12 pre-calculus mathematics, including arithmetic, algebra, geometry, and trigonometry. And it gives us some very powerful tools for examining the behavior of functions. This leads it to being used in many applications in many fields, including various areas of mathematics and statistics, physical and biological sciences, business, medicine, engineering, and many other fields. If pre-calculus is like a hammer and a handsaw, then calculus is like a set of power tools. Oh yeah, you can do a lot with calculus. There are two main areas of calculus: differential calculus and integral calculus. Differential calculus concerns slopes and rates of change, whereas integral calculus concerns area and accumulation. They are both based on one fundamental concept of calculus, the limit. And these two branches of calculus are related to each other in an inverse sort of way by the fundamental theorem of calculus. This set of notes and the accompanying YouTube video, this video, is designed to give a concise, compact overview and review of the main differential calculus concepts and skills from Calculus 1. So this material makes good review to use at the end of a Calculus 1 course before taking the final exam. It also makes a good review at the beginning of a Calculus 2 course before diving into new material in that course. This is not intended to be a first introduction to these topics. I have a full set of lecture videos on many classes, including pre-calculus material from algebra and trigonometry, some geometry, and videos for calculus sequence. And these are found on my YouTube channel, which you can see a link to there. Which is, of course, where this video is also located. The concepts in these notes are developed more completely, more slowly, and in more detail, and with many, many more examples in the following playlist from my calculus videos. You're strongly encouraged to review all or portions of this material as needed. The differential calculus part of Calculus 1 I have as units 1, 2, 4, and 6 that you can see there. In Unit 1, we cover limits, continuity, and a survey of elementary functions. In Unit 2, the derivative definition and concepts are gone over there, introduced. In Unit 4, we talk about the derivative formulas and working with them, developing and using shortcut rules there. And then Unit 6 is all about applications of derivatives. So the goal here in this set of notes in this video is to reduce hundreds of pages of notes and many hours of lecture video to a concise review in this single set of 20 typewritten pages of notes in this single video. We'll see how short I can make the video. The direct link to the video, if you have the notes, can be obtained by clicking that link. So to start, we need to talk about limits and continuity. The one fundamental concept that forms the foundation of all calculus is the concept of a limit. The use of a limit is what turns pre-calculus into calculus, and every calculus concept has at least one limit behind it somewhere. And so basically a limit is just saying that as the input value of a function gets closer and closer to a specific value, the output is also getting closer and closer to some possibly other specific value. And here's the notation for some types of limits. This first one we read as the limit as x approaches 0 of f of x equals 5. This indicates as the input x gets closer and closer to the value of 0, the output gets closer and closer to the value of 5, the output being f of x or f or y. So the graph is basically getting closer and closer to the point 0, 5. So 0, 5 is a limit point. If the point 0, 5 is actually on the graph, then the function is continuous at that point. And if the function 0, 5 is not on the graph, then the graph has a hole in the graph, also called a removable discontinuity at 0, 5. But notice that the limit has nothing to do with what the value of f is when x equals 0, or if that value even exists. The function may not exist there, or it may have a different value than 5 at that point. And that's okay, it has nothing to do with the limit. It's what's happening near x equals 0. We can also do limits going to infinity or minus infinity. The limit as x goes to infinity of f of x equals 7 indicates if we let x go toward infinity, meaning getting bigger and bigger and bigger and bigger, we're going further and further to the extreme right on the graph, then the y values are getting closer and closer to 7. One of several possibilities is that y equals 7 is a horizontal asymptote. There are other possibilities as well. if we say the limit as x goes to 5, and that minus sign there means from the left side of f of x equals 4, this is a left-sided limit, a one-sided limit, where the graph approaches the point 5, 4 from the left side. We're not saying anything at all about what happens to the right of 5. For a function to have a full limit, the left and right limits must exist and be the same. So one way you can get a place where we don't have a full limit is to have what was called a jump discontinuity, where you get different limits from both sides. This one here is a limit from the right side, but we have infinity here. So the limit as x goes to 5 from the right side of f of x equals infinity is one way that a limit might not exist. This doesn't really say the limit exists. It explains how it might not exist. And in this case, the x's values are all larger than 5, but getting closer and closer to 5, and the y values are just getting bigger and bigger and bigger and bigger without bound. And so this is a vertical asymptote. So x equals 5 is a vertical asymptote with the graph going up on the right side of that. Continuity is important. We say that a function f is continuous at a point x equals a if and only if the limit as x approaches a of f of x equals f of a. Notice this requires three things. The function f must exist at a, f of a exists, and the limit must exist, and then those two things must be the same. So graphically, what this turns out to be is you have the point a comma f of a on the graph, and if you draw a small enough circle around that graph, around that point, then all of the graph is one connected piece in that circle. And we can see different types of limits graphically in the following example. So you might pause the video and try to work out some of these yourself. Some videos, some limits that might present themselves here. So let's do a few of them. The limit, it's just f of negative 6 is the y value when x is negative 6, and there isn't one, at least not one here on the page, and we'll say there's not one at all. And so we say that does not exist. But the limit can and does exist there. The limit as x goes to negative 6 here is 4. Whether we're coming from the left side or the right side, as the x's get close to negative 6, the y's get close to positive 4 there. F of negative 5, let's see, where is that? Is actually down here at negative 3. Should be an open dot at the end of that one here. But the limit as x goes to negative 5 actually does not exist. And the right limit does exist. So the limit as x goes to negative 5 from the right side is 0. So this is getting closer and closer to y value of 0 from the right side. From the left side, it's approaching infinity. So we have a vertical asymptote there. And this on the left side by itself would be enough to say that the limit doesn't exist, but the fact that they're not the same limits from both sides definitely says that we don't have a full limit that exists there. F of 0 is 5, that's the 0.05 right there, and the function is actually continuous there, so the limit as x goes to 0 is 5, and we see that it's a connected piece near that point. Let's see, what else do we have here? F of 5 is negative 2. Yeah, that's down here. It's very similar to the one on this side. In this case, we have left and right limits, but they're not the same. This would be a jump discontinuity. The limit from the right as x approaches 5 from the right side is negative 5, and the limit as x approaches 5 from the left side is 0. And then f of 5 is negative 2. So those are all three different values there. Right here we have the function is left continuous, so that the y value is the same as the left limit, but the right limit's not the same. The limit from the right side is 3, and the limit from the left side is 2, and those are not the same, so we have a jump discontinuity here. We can also talk about what's so-called end behavior. It's kind of a misnomer because this doesn't really actually have any ends to it. It goes forever to the right and forever left. But as we go out to the right forever, it looks like the limit might be 0 here because the limit as x goes to infinity is 0. That says we have a horizontal asymptote there. And we can more clearly see the limit as x goes to negative infinity here is 3, which are given by some of those things. We can also informally find limits through the use of tables of values. For example, the following values indicate that we have y values, x values, or t values, excuse me, input values, getting closer and closer to 4. 3.9, 3.99, 3.999. Those are getting closer to 4 coming from below, and these here are getting closer to 4 coming from above. 4.01, 4.001, 4.0001. So as we're approaching the middle of the table here, the x values or t values, input values, are getting closer and closer to 4. And if you look at what the y values are, it looks like they're approaching 7 from both sides. So now that we have the idea of a limit, we want to go on and define a derivative. In general, we obtain calculus concepts by taking a pre-calculus concept and applying a limit to it. The derivatives are found by applying the limit concept, a limit to the concept of a slope. Of course, we've been doing slopes since at least Algebra 1, if not before. And really, differential calculus is really just studying slopes. This turns an average rate of change, a slope, into an instantaneous rate of change, which is the derivative. For example, if we want to find the instantaneous rate of change in position, instantaneous velocity, at a time x equals 4, then we are finding the derivative of the position function at time x equals 4. And we can approximate this from a table of values by approximating it with an average rate of change. So in this table, we have x equals the time, and here we have times at 0, 2, 4, 6, and 8. And then we have their corresponding positions, 5, 10, 18, 25, and 39. So this might be times of days, maybe hours. After a certain, say, afternoon, that might be noon, 2 o'clock, 4 o'clock, 6 o'clock, 8 o'clock. And these might be mile markers, say, on an interstate. Okay. If we use the slope formula using the point x equals 4, this red one, and another nearby point, say this blue one here, we're finding what's called a difference quotient. The difference quotient approximates the derivative at 4 using the slope formula with the point of interest, 418, and a nearby point, this is 625. And this is uses an h of 2, which is the delta x, how far we changed x. So we went from 4 to 6. 6 minus 4 is 2. So that's the delta x, or h. Okay, and the general formula is the difference quotient will be a change in the function over a change in x, delta f over delta x. And that is f of a plus h minus f of a, and h is another name for delta x. Of course, delta x, like we said, is 6 minus 4 is 2. And then a is 4. So f of a is its corresponding y value, which is 18. And a plus h is 4 plus 2, which is 6. And then we do f of that, which is 25 here. In other words, we're just doing good old y2 minus y1 over x2 minus x1, the good old slope formula back from Algebra 1. So that's a vertical change or rise of 7 and a horizontal change or run of 2. So our slope is 7/2 or 3.5. Again, here h is delta x. And so it's nothing more than just taking these two things and find the slope. So what we have here is a slope of between 2 points on the table, 2 points on the graph, slope of a secant line across there. So a better approximation of the derivative using the same value of h would be to use the slope formula with points on either side of the point of interest. Use the green and blue points here, not use the point of interest. Turns out that the slope across there turns out to be the same as averaging the slope of these 2 points and the slope with these 2 points. So let's work that out. That's called the symmetric difference quotient. And the symmetric difference quotient is our best estimate of the derivative from the information that we have here. So the symmetric difference quotient, again, is just a delta f over delta x, but this time it's f of a plus h minus f of a minus h, and delta x is 2h. So we're using these 2 points. That's 25 minus 10 over 6 minus 2. Okay, so h is still 2, but then it's 2h across here, which is 4. And 25 minus 10 is delta y, or delta f, which is 15. So our slope is 15/4, or 3.75. And that's going to be our rate of change. So this would be, say, maybe, miles per hour here, or maybe it's some other units, feet per second or whatever. Both the difference quotient and symmetric difference quotient are average rates of change in the function over an interval. The difference quotient has the point of interest as one endpoint of the interval, and the symmetric difference quotient has points on either side of the point of interest as endpoints of the interval. Graphically, these are slopes between 2 points on the graph, or as a slope of a secant line. So here is the difference quotient of a function. Here's the function right here, 1/20th x times x minus 6 times x plus 4. That's this cubic graph right here, and I've picked an input of a is 4, and so we take that right there. There's a comma f of a. We've picked an h of 1.5, so I'll go to the right 1.5 from there, come down and find the y value there. Then you just do the slope across there. It's the delta y is this yellow distance, delta x or h is this distance, divide those two, and we get the slope of that secant line, which is worked out in detail right over here, and it turns out to be 1.2625 is the slope of that little purple line. Okay. Here is the symmetric difference quotient at the same point, illustrated as a slope of a secant line. This time, instead of taking our point of interest down here and finding the slope between it and a nearby point, which is what we did here, what we do is we go equally either side of this to find the points where x is a minus h and x is a plus h. There's the symmetric part that's the same distance from a horizontally, not necessarily vertically. And we find the corresponding y values there to find points on the graph here at a minus h comma f of a minus h and a plus h comma f of a plus h, and do the slope across there. Notice this time delta x is twice h, so here's h is 1.5, so we're going to actually be dividing by twice that, which is 3 here, and then we just find the vertical change here by subtracting the two y's. You can see the details worked out over here for these specific numbers, and we get a 0.5125. So in this particular one, I used a pretty large h, so neither one of these may be that good of a guess or an approximation, but in fact the symmetric difference quotient is going to be the better of the two for the same h in most cases. But in either case, we can take a limit as the value of h approaches 0 to obtain the derivative. Since we want functions that are undefined at a point to have a derivative being undefined at that point, we use a difference quotient, not the symmetric difference quotient, with the limit as the definition of the derivative, even though the symmetric difference quotient gives us the better approximation. So the derivative of a, denoted by f prime at a, or by df over dx such that x equals a, is defined to be equal to the limit as h goes to 0, f of a plus h minus f of a over h. So the derivative of the point is actually a number, and it's a number which is the instantaneous rate of change in the function at a particular point. It's the slope of the curve at a single point, which notice doesn't really make sense with pre-calculus because the slope formula requires 2 points. But it does make sense here because it's the slope of the tangent line. These lines here, both the tangent line here and up here, get closer and closer to those secant lines up there, get closer and closer to this tangent line as h gets smaller and smaller. And in fact, the slope of that red tangent line then, in this case that's 0.4, is the actual derivative. Here I use a pretty small h, 0.001, and we see that both the difference quotient and the symmetric difference quotient are very close. In fact, it's to the number of digits I have rounded here, they're identical with the symmetric difference quotient. But that's the slope of that tangent line is the derivative. So to approximate the derivative point, it's best to use the symmetric difference quotient. We saw how to do this from a table up above. If we have a graph, we just identify 2 points equally to the right and left of the point of interest, but nearby, find their coordinates, and apply the slope formula. So if we want to approximate f prime at 4, we can go a little bit to either side. Say if we go to the grid line here, let's see, is that what I used? Actually, no, I tried to go halfway. Halfway between the grid lines, I went to 4.5 and come up here and estimate the y value here. And I went to 3.5 and estimate the y value there. And then just do the slope. So the 4.5 and 3.5 gives us a delta x of 1. And delta y, I estimated that at 4.5 to be 1.8, and at 3.5, I estimate to be 3.5. And I'm estimated to be 0.5, excuse me. And then subtract and get 1.3 for a change in y divided by the 1. That's 1.3. Actually, since I know the formula of this, I know it's exactly when you round off to three significant digits, 2 decimal places, it's 1.24. So that's 1.3 is actually pretty close. If we have a formula in a calculator, then we can use a symmetric difference quotient with a very small h. We're not limited to something that we can easily measure in a calculator, or measure on a graph, or look at it in a table. We can put in something really small. So for example, if we have f of x equals 3 times x to the x power, if we want to approximate f prime at 2, we can do f of 2 plus h minus f of 2 minus h over 2h, a symmetric difference quotient, and just make sure we use a small h. So the formula is 3x to the x power, so it's 3, 2 plus h to the 2 plus h power, and 3 times 2 minus h to the 2 minus h power over 2h. And here I just plugged in an h of 0.001 everywhere and worked out the details, which here it is on a calculator. Of course, I'm using a calculator to do the arithmetic here. Didn't want to do this stuff by hand. And it gets approximately 20.31778045. Now it turns out that TI graphing calculators have this approximation technique built in. In other words, they have a symmetric difference quotient built in. For example, on a TI-84, use Math 8 to get a numerical derivative, which is a symmetric difference quotient. On the newer calculators, it looks like Leibniz notation for derivatives. The d over dx of, you put your formula in here, 3x to the x power, such that x equals, and then you put in 2. This is, you put the variable x here, formula here in terms of x, and then you put the x value here. And look, it's the same thing as that, exactly the same numbers. So that's what it's doing. It's doing a symmetric difference quotient with 0.001. If you turn it to the older operating system or turn MathPrint off, you can actually, it's numerical derivative. It looks something like, numerical derivative. You put in the formula, 3x to the power x. You put in the variable x, you put in the x value, and then you can put in, optionally, you can put in the h value. And by putting in the smaller h value, you can, maybe get possibly a better answer. It defaults to 0.001 if you leave that off. So notice that the derivative is a number, a specific number, okay, provided it exists. Of course, limits may or may not exist. However, if we let the input be a variable x, then the derivative of a variable x is a new function derived from the original function called its derivative function. The result is the following formula. The following is a formula in terms of x for the derivative function, the first derivative function. So f prime of x, or df over dx, is a formula in terms of x, where we have f of x plus h minus f of x over h, and take the limit as h goes to 0. So at any x value, that value of f prime of x is the slope of the graph of the original function at that point. In other words, the slope of the tangent line. So here we have the original function in blue, and at each of these points where I have a little green dot, it's the slope of this little tangent line segment. If I had those perfectly on the line, they would be the slope of the tangent line to the curve. And we would get those, we do that for infinitely many points, we get the graph of the derivative function. Now, what we want to be able to do is maybe find the formula for that derivative function if we have the original formula, or formula for the original curve. Okay, original function. And what we do there is we actually take a limit of difference quotient. So if we have f of x equals 3x squared minus 2x plus 7, If we use the definition of the derivative directly, no shortcut formulas, to derive the formula for the derivative, then what we're doing is just applying it like this. F prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. F of x is 3x squared minus 2x plus 7. Put that in parentheses. There's a minus, parentheses here, h in the bottom, limit as h goes to 0. And the first parentheses, just like the second one, but the x's have been replaced by parentheses, x plus h right there. Now, it's a whole bunch of algebra. Okay, so we square this out. We get x squared plus 2hx plus h squared. You might use FOIL for that to help you remember the distributive property. Then distribute the 3 here, negative 2 here, and then the negative 1 here. Then what happens is all of this part at the end is going to end up canceling. The 3x squared cancels with the negative 3x squared. The 2x cancels with that negative 2x. The negative 7 and the 7 cancels, leaving these terms in the top. Now we notice they all have a factor of h, so we can factor that h out using the distributive property. Common factor, factoring, and cancel the h's because this reduces to this as long as h is not 0. Well, wait a minute, h is approaching 0, but that doesn't mean h is 0. In fact, very specifically, we want to make sure that h is not 0 there, but only stuff that's close by. Now, this is a continuous function of h, so now we can actually just plug in h is 0 and work this out to be 6x minus 2. Now, I know all of you know a shortcut to this, but when you're doing a derivative, this is what actually is going on in a derivative. It is a limit of difference quotients. However, this is rather tedious for something this easy, and especially could be really nasty if we want to try and find the derivative of a more complicated formula. So what we like to do is find some general situations that occur a lot and derive and prove some general derivative shortcut rules. For example, we can apply the techniques above to derive a sum rule. The sum function, s of x, is the sum of the functions f and g. So s of x is f of x plus g of x. Well, that's the limit as h goes to 0 of s of x plus x minus s of x over h. S of x is f of x plus g of x. S of x plus h is f of x plus h plus g of x plus h. Well, dropping these parentheses and distributing the minus here gives us this. Using the commutative property, we switch these two. Using the associative property, we group this together and we can distribute the h here so that we get two fractions. And we have a property of limits. Says the limit of the sum is the sum of the limits, provided those limits exist. The first limit is f prime, the second limit is g prime. So what we found is the derivative of the sum of f plus g is f prime plus g prime. The derivative of the sum is the sum of the derivatives. And so doing this for many other situations lead us to a variety of shortcut rules, sum rule, product rule, quotient rule, and so forth. And in particular, the chain rule, which could also be known as the substitution rule or composition rule, is used in conjunction with other rules to allow us to find derivatives of practically any function we can write down. And here's a list of some of those basic derivative shortcut rules. And you should have these memorized, at least everything that's in black, maybe not the blue parts, but the black parts you should definitely have memorized. Below, f, g, u, and v are functions of x, and b and n are constants. And I've done substitutions, so the chain rule kind of permeates things here. So the sum rule that we just proved was the derivative of f of x plus g of x is f prime plus g prime. The derivative of a constant times a function is a constant times derivative function, the constant multiple rule. The product rule gets a little bit more complicated. The derivative of f times g is f times g prime plus g times f prime. First factor times the derivative of the second factor plus the second factor times the derivative of the first. And this generalizes to 3 or more terms. If you have 3 terms here, you take the derivative of the first times the other 2, plus the derivative of the second one times the other 2, plus the derivative of the last product factor times the other 2. Or this is a more complicated way of saying this thing works for no matter how many terms we have. The quotient rule, derivative of f of x over g of x is g f prime minus f g prime over g squared. Or the way I like to say it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. The chain rule, also known as the composition or substitution rule, is the derivative of f composed g of x, that is the derivative of f of g of x, is f prime evaluated at g of x times g prime of x. or the way you actually do it, is you make some substitution where u is a function of x, and you rewrite the function as f of u, but you're taking the derivative with respect to x. So what you do is just take the derivative of f of u in terms of u, so you get f prime of u, but since u and x did not match, you multiply by du over dx. The inverse function rule comes in handy sometimes. The derivative of f inverse of x is 1 over f prime evaluated at f inverse of x. In other words, it's 1 over the derivative of u, derivative with respect of u, of f of u, but then evaluate where u is f inverse. That allows us to find formulas for things like logarithms or inverse trig functions where we know the derivative of the original function. We're trying to find the derivative of the inverse function. So notice these don't really find a derivative. They reduce it to another derivative problem. If you notice, the right side has still got a derivative in it. But now we have certain formulas types of functions that we can actually find the derivative of. The derivative of a constant is 0. The derivative of a constant times x is just c. It's just a constant. We have a generalized power exponential rule that says the derivative of u to the v. Now notice we've made two substitutions. U and v are both functions of x. Okay? The first part is you get v times u to the v minus 1 times the derivative of the u. Plus we get the log of the u times the original function u to the v times the derivative of v. Now if you look, if v is a constant, then this part goes away, that last part's 0, and you get what's called the power rule. The derivative of u to the n is n times u to the n minus 1 du. Whereas if the u is 0, is a constant, then this du over dx is 0, and you get the exponential rule. The derivative of b to u is natural log of b times b to the u power times du over dx. A special case of that is when b is e, our specific base, standard base for an exponential function and logarithm. Natural log of e is just 1, and so the derivative of e to the u is e to the u times du over dx. The derivative of logarithm of absolute value of x is 1 over u times du over dx. If you don't have the absolute value, the derivative of log of u is 1 over u times du over dx, but you have to restrict it for u being positive, because 1 over u would be defined for positive and negative u, whereas log of u is only defined for positive u's. Then we have our basic trig functions, circular trig functions. The derivative of sine of u is cosine of u times derivative of u. Derivative of tangent u is secant square of u times du over dx. And the derivative of secant u is secant u times tangent u du over dx. And if you know those, it's easy to get this other one, because if you change sine to cosine, you change the answer cosine to sine, tangent to cotangent, change secant to cosecant, secant to cosecant. Here you change this to cosecant and cotangent, but any of these that start with a co also have a negative factor out front. So if you memorize these three on the left, the three on the right are easy to get. Then we also found some hyperbolic trig functions. They're probably not used as much, but we have a simple rule there for them. The derivative of hyperbolic sine of u is hyperbolic cosine of u. Derivative of sinh of u is cos of u times du over dx. And then derivative of cos u equals sinh of u du over dx. And you can see the other hyperbolic trig functions here. They're very similar to the circular trig function rules, but minuses show up in a little bit different places. Maybe a little bit more important are derivatives of inverse trig functions. Derivative of arc sine of u is 1 over the square root of 1 minus u squared times du over dx. And the derivative of the arc tangent of u is 1 over u squared plus 1 du over dx. And you can also see in blue some of the other basic inverse trig functions. You should at least memorize these ones in black. And then here you have some for inverse hyperbolic trig functions. And that is a pretty complete list. So if you know all of these rules, you can basically find the derivative of any function that you could possibly come up with by using these in conjunction with each other. Okay, so let's use the derivative shortcut rules and do a couple of examples here. So here are just a few examples. For example, the derivative of this function, 3 to the x power times parentheses 4x squared plus 6x minus 5. Using the product rule, it's the first times derivative of the second plus the second factor times derivative of the first. Derivative of this part here is pretty easy with you've got polynomial functions like this, or even sums of power functions. Since you use this combination of rules here, but it's pretty easy. You take the power, 2 times the 4 is 8. Power goes down to 1. For an x term here is just the coefficient. The constant term derivative is 0. Derivative of an exponential function is the original function times the logarithm of the base. And there it is. I did notice that they both had a 3 to the x power, so I factored that out front. And that gave us this term, 8x plus 6, and then this term and this term. And then I just saw that this was actually a polynomial. I have 4 log of 3 times the x squared. And for the x term, I have 8 plus 6 log of 3 for the x coefficient of the x. And the constant term, I have 6 plus a negative 5 log 3 there. That used the product, well, several rules, but the product rule was our starting thing. So how do you know which rule to use to start with? Well, look at the outermost structure of the function. The last step in evaluating this is multiplication. So use the multiplication or product rule. The last step in evaluating this function is division. So we use the division or quotient rule. Quotient rule says it's the bottom times derivative of the top minus the top times derivative of the bottom over the bottom squared. You're just going to leave the bottom like it is. Factored. The derivative here is 6x plus 2. The derivative here is just 5. Distributing this out through FOIL here, you get 30x squared minus 32x minus 14. Distribute the negative 5 here, you get negative 15x squared plus negative 10x plus 20. Combine like terms, 15x squared minus 42x plus 6. And we'll factor a 3 out of that. And there's our final answer in factored form. This top doesn't factor unless we go beyond the rational numbers there. Go to real numbers or maybe even imaginary numbers. Okay, complex numbers. The derivative of cosine of 2x cubed. This is a good example of using the chain rule. So you have to let u be 2x cubed. When you do that, then we've got the derivative of cosine of u. Well, du over dx is then 6x squared. So the derivative of cosine u is minus sine of u, but since we did a substitution, we used the substitution rule, in other words, the chain rule. That means we have to multiply by du over dx. So the du over dx we saw is 6x squared. The u is 2x cubed, and there's the answer. Usually we'll write that part in front. So our final answer is negative 6x squared times sine of 2x cubed. Here's the one where we use the chain rule twice. I'll let u be sine of 2x squared minus 1 so that we just get the derivative of e to the u. So the answer is e to the u times derivative of the u. Well, I want to let v be the 2x squared minus 1, and u then becomes sine of v. And so this is the derivative of sine of v. Well, the derivative of sine of v is cosine of v times the derivative of v. Well, the derivative of that v is 4x. Cosine of v, substitute that back in, we get that. Substitute this back in for u, and I just reordered the terms a little bit here. And our final answer is 4x times e to the power sine of 2x squared minus 1 times, the whole thing is then times cosine of 2x squared minus 1. Here's one where we use that generalized product exponential rule. Okay, we have a variable base and a variable exponent. Well, you treat it like it's a power function. You do the power times the base and subtract 1 from the power. But then you take the derivative of the base, which is just 4. Plus, you treat it like it's an exponential. Leave the function alone, but multiply by the derivative, multiply by the base, and then by the derivative of the power. Here, that power is 5. Okay, so let's see what we've got here. Notice that this is a 4 and an x is the same as that, so it's 4x to the first times 4x to the 5x plus 1 minus 1, add exponents, that's 4x to the 5x. And we still have the 5. Now, if you look at this, they both have a 5. They both have a 4x to the 5x. So I'm going to bring that out front, factor it, leaving it just a 1 here. And what's left here is the log, natural logarithm of 4x. Here's one where I do a couple of substitutions. Let u be 3x plus 2 and w be 4x minus 7. Then I've got the derivative of u to the 5th times w to the 8th. So that's a product rule. First times derivative of the second plus second times derivative of the first. This is 8w to the 7th times the derivative of the w. This is 5u to the 4th times the derivative of the u. The u is 3x plus 2, so that derivative is 3. The w is 4x minus 7, so that derivative is 4. Let's see what we can factor out of this. The 4, 8, all this, no number parts in common, so this is just going to be 32 and this is going to be 15. So I did that. But then the u's, they have a u in common, 4 of those, and 7 w's. So u to the 4th, w to the 7th can be factored out. That's left with 32u plus 15w. Substitute back in, u is 3x plus 2, and w is 4x minus 7 there. Distribute, we get 96x plus 64 plus 60x minus 105. Combine like terms, that's 156x minus 41. Substitute back in the u and w right there into here. And our final answer is f prime of x equals 3x plus 2 to the 4th times 4x minus 7 to the 7th times 156x minus 41. The factored form is pretty useful there because one of the things that we want to find often is when the derivative is 0. Now, on one hand, finding derivative formulas and using the shortcut rules is the least important part of calculus 1. Since a calculator with a computer algebra system, such as a TI-89 or TI-Inspire CALC, or various computer programs such as GeoGebra, Wolfram Alpha, Symbolab, and others, will compute the formula for any derivative. Some of these will run on computers, tablets, and even smartphones. So in fact, you already have a smartphone in your pocket or purse. You have a device that can find the derivative of even the most complicated function. You can probably even just call on your voice assistant, Siri or whatever, and ask, and it will tell you the derivative of any function you want. So making the skill somewhat unnecessary on the one hand. But on the other hand, being able to compute and simplify derivative formulas without the use of technology really, in a way, does get at the heart of one of the main things, or some of the main things, that we're trying to teach in calculus. Some of these main things include learning how to apply challenging algorithms, persevering through multi-step procedures, being comfortable with formulas, and demonstrating a strong work ethic. Attention to detail and some other things. These and similar broad skills are the main reason we want to study any part of calculus. So in a way, that's the most important part of the course, rather than they're much more important than any specific calculus skills themselves. So yeah, this is still kind of important. All right, moving on. What's more important than just finding these formulas, though, is learning how to apply them and understanding what they mean. We're going to talk a little bit next about higher order derivatives and graphing. Since the first derivative function is itself a function, it has a derivative as well. We call the derivative of the derivative the second derivative of the original function. We call the derivative of the second derivative the third derivative of the original function, and so on. In particular, the first and second derivatives tell us a great deal about the graph of the original function. Continuity and local linearity. First of all, a function must be defined at a point to be continuous there, and it must be continuous there for the derivative to be defined there. Just knowing that the derivative exists at a point tells us that the function exists and it is continuous at that point. Furthermore, if we zoom in very close near a point on a function where it's differentiable, the function looks very much like a non-vertical tangent line to the curve at that point. So basically, it looks kind of like a line if we zoom in close enough. We call this property local linearity property of differential functions. Now, the first derivative tells us about the direction of the original function. More specifically, if the first derivative is positive at a point, then the original function is increasing at that point. If the first derivative is negative at a point, then the original function is decreasing at that point. If the first derivative is 0 at a point, then the original function is at what we call a stationary point, and that means it has a horizontal tangent line there. If the first derivative is 0 and the second derivative is positive, then the original function is at a local minimum. If the first derivative is 0 and the second derivative is negative, then the original function is at a local maximum. If the first derivative and the second derivative are both 0, then the function is either a local extremum or an inflection point, but more information is needed to see which is going to be. If a function is at a local extremum, then one of the things has to happen. Either the first derivative is 0, or the first derivative is undefined, or the function is at an endpoint. Concavity is what the second derivative tells us. The second derivative tells us the direction of the first derivative and the concavity of the original function. So if the second derivative is positive at a point, then the first derivative is increasing and the original function is concave up at that point. If the second derivative is negative at a point, then the first derivative is decreasing and the original function is concave down at that point. If the second derivative is 0 at a point, then the first derivative is at a stationary point and the original function may have an inflection point there. If the second derivative is 0 and the first derivative is non-zero, then the original function is definitely at an inflection point. If the first and second derivatives are both 0, once again, the function is either a local extremum or an inflection point, but more information is needed to see which one. If the function's at an inflection point, then the second derivative is either 0 or undefined. There's some interesting points on graphs, and some of these are called critical points. Interesting point on a function can include when it has a discontinuity, is at an endpoint, or when it crosses the x or y axis, when it's at a local extremum, or when it's at an inflection point. To find these, we identify whether the function, its first derivative or its second derivative, are either undefined or equal to 0. And between these interesting points, the function is fairly well behaved. So we can see these relationships among the interesting points and the graphs of the following polynomial function. We have a cubic polynomial function, and we have its first and second derivatives, and we can see those. So for example, the blue one here is the original function, which is a cubic. Negative 3, 0, negative approximately 1.40, and 1.410, and 1.410 here. Those are the x-intercepts. These two here are approximated. Then we have a y-intercept of 0, negative 6, which is pretty easy to see. And then its derivatives given by this red one here. Notice when the derivative is at 0, approximately negative 2.29 and positive 0.29. That's the x values of the extremum here, the local maximum over here in the third quadrant, and the local minimum in the local maximum in the second quadrant, local minimum down here in the fourth quadrant. Notice when the derivative is positive here, the original function is increasing. Then from here to here, the original function is decreasing. The derivative will be negative. And the derivative is positive. The original function is increasing. The second derivative is the derivative of the first derivative, so that's the green one here. And it crosses the x-axis at one time at negative 1, 0. And that negative 1 then is the x-coordinate of the extremum, the minimum here on the first derivative, and it's the x-coordinate of the inflection point on the original function. Here you can actually see the formulas. It's polynomials. It's not too hard to apply our rules here. 3x squared plus 6x minus 2 for the first derivative, and then 6x plus 6 for the second derivative. It's easy to set that equal to 0 and see that x is negative 1. Use a quadratic formula on that to find the exact values of these 2 points here, which are approximated. So an exercise would be to see if you can solve these things and find the exact coordinates of all these things. But if you notice, this is all the really interesting stuff. When the second derivative is negative here, the original function is concave down. It switches over at this inflection point to concave up. That's when the second derivative is positive. Second derivative is positive. The first derivative is increasing. Original function is concave up, and so forth. So between these interesting points, you sort of got well behaved. On this last piece, it's increasing concave down, then it's decreasing concave down to the inflection point. Between this inflection point and extrema, it's decreasing concave up, and then from there on, it's increasing concave up. Now, the real power of derivatives is looking at applications. And it's a really cool intellectual exercise to talk about calculus and so forth. But the real thing that makes people want to use it is its power in doing applications. And there are many applications of calculus. In fact, this is what makes calculus such a popular subject to study, and why the K-12 curriculum is focused on primarily on preparing students to learn calculus. For good or bad, that's the way it is. And some of the most basic applications of derivatives focus on interpreting the derivative as an instantaneous rate of change in the context of some real-world scenario, or applying the local linearity property. So let's talk about what I mean by that and how to visualize the derivative. We can visualize the derivative f prime of a as actually an actual distance. We've talked about it as a slope of a line, a tangent line, but we can actually see it as a distance too on the graph. Vertical distance. It's the amount the tangent line goes up when we go to the right one from a point of interest. So the derivative at a, you follow the tangent line 1 unit to the right, and however far it goes up, this black distance right here is f prime of a. Compare and contrast that to how much the function changes when you go to the right one. That's this green distance here from here to this nearby point here. Of course, that's going to be the slope of the secant line across between here and the nearby point, the slope of which is the difference quotient. So the difference quotient is delta y when h is delta x is 1, and the derivative is the vertical change delta y on the tangent line. So it's a difference in the change on the tangent line versus the change on the secant line. So I want to point out these are certainly two different values, but I also want to point out that they're typically relatively close to each other. And so we often use one to approximate the other. So it's often seen in many applications, for example, in business applications. In business applications, you'll see the word marginal used to indicate a derivative. For example, the marginal profit at a point is the derivative at that point. But it's also approximately the same as the amount of change in the profit when we increase the production by 1 unit. In other words, increase the input by 1 unit, it's how much the output goes up or down, up, positive, down, negative. And this is an application of this local linearity idea, since the approximation would be exact if the function was exactly linear. And remember, differential functions are not linear usually, but they're usually approximated well with the linear function, the tangent line, if delta x is 1, or delta x is small, and delta x is 1 is relatively small. So let's see how we can put that into work in a few examples. So let h be the height in inches of Dr. Jackson t years after my birth. What are the units of h prime of t, and what can you say about the signs of h prime of 10 and h prime of 30? Well, h prime of 10 is positive since my height was increasing on my 10th birthday. And so that would be the how fast I was, h prime of 10 would be how fast in inches per year I was growing on my birthday, my 10th birthday. But g prime of 30 is 0 because I was neither increasing nor decreasing in height on my 30th birthday. I'd already reached my grown-up height and was not shrinking any at that point. In general, the units of the derivative are the output units divided by the input units. So in this case, the units are inches per year. All right, here's another example. The chief financial officer of a company reported that during the previous quarter, profits continue to increase, but at a slower rate. If P of t gives the company's profit at time t, what can you say about the signs of P prime and P double prime? Of course, we hope the sign of P prime, of just P of t, is positive, because we hope they're actually making a gain rather than a loss. But since the profits were increasing, the function P of t is an increasing function, and that means P prime is positive. And since the profits were increasing, however, at a slower rate, that means that P prime is decreasing, and then P is concave down, and that means that P double prime is negative. All right, let's try another example. Suppose that W of V represents the degree of wind chill and the velocity of the wind is V. What are the units of W prime of V in the United States? And interpret the information provided by W prime of 20 equals negative 0.2 and W double prime of 20 is greater than 0. And explain the meaning of the signs. Well, wind chill is kind of a miserability index because it's sort of what it feels like. So now in the United States, we measure temperatures in degrees Fahrenheit. Yeah, I know we're backwards from the rest of the world, but that's what we do. And we measure velocity of the wind in miles per hour. So appropriate units for W are degrees Fahrenheit and miles per hour for V. So the units of W prime of V will be the units of W divided by the units of V, that is degrees Fahrenheit per mile per hour. So W prime of 20 equals negative 0.2 means that increasing the wind velocity from 20 miles an hour, 1 unit, to 21 miles per hour would result in a wind chill dropping approximately 0.2 degrees Fahrenheit. In other words, it would feel 0.2 of a degree cooler, even though we're holding the actual temperature constant here. We should know that W prime of V is negative since increasing the wind velocity results in a perceived drop in temperature, in other words, a decrease in wind chill. W double prime of 20 is greater than 0 means the graph of W is concave up, and we already knew it was decreasing. So a concave up decreasing means that it's going to drop more at first and less later on. So we see that W is decreasing at a decreasing rate. In other words, going from 20 miles an hour to 21 results in a drop of about 0.2 degrees, but going from 21 to 22 would result in a slightly less of drop, say maybe 0.1 degrees. One of the most powerful areas of applications of derivatives is the area of optimization problems. Often we want to push something to the extreme. We want to minimize costs, maximize revenue, or better yet, maximize profit. We know that the local extreme of a function occur at endpoints where the derivative is undefined or where the derivative is 0. So derivatives can help us find optimal conditions. So here's an example. A typical soda can holds 355 milliliters, 12 fluid ounces, and is roughly the shape of a cylinder. The thickness of the top of the can is 3 times as thick as the sides and the bottom of the can to accommodate the pull top opener. What dimensions will minimize the amount of aluminum used in the production of the can? So the volume is fixed at 355 milliliters. A milliliter is a cubic centimeter. And this gives us a relationship between the radius and height of the cylinder. Well, the volume is the area of the base times the height. The base is a circle, or area of pi r square, where r is the radius, and h is the height. So the height is right here, or right here, and the radius is this part. But the volume is constant, so we can solve for h. H is v divided by pi r squared. V is fixed at 355. So we have h as a function of r. Now the amount of aluminum used is actually a volume, but it's based on a surface area. So if we have T as the thickness of the sides and bottom, so 3T is the thickness of the top. So the top and bottom are the interior of the circles, which have areas pi r squared. And if you cut it down the side and roll out the side flat, we get a rectangle whose height is h, the height of the cylinder, and whose length is the circumference of the circle, 2 pi r. So if we put that together, the area is 3t times the area of the top, or 3t pi r squared, t times the area of the bottom, t times pi r squared, and t times the area of the side, 2 pi r h. Now, let's see, we put these together and get 4t pi r squared and plus 2t pi r h. But now h is 355 over pi r squared, so I can substitute that in here and do a little canceling here. Cancel these r's out and make that r to the negative 1. 2 times 355 is 710. So here we have a strictly as a function of one variable, only r. Remember, t is a constant. So if we take the derivative now, a prime of r, remember t is a constant, so this is just a sum of power functions. Take the power times the coefficient, 8t pi r, minus 710 t r to the negative 2, and set that equal to 0. So what I'm going to do first is multiply both sides by r squared over 2t, and this is going to simplify some things for me. So the left side's still 0. Here they both had a 2t in common, so this dividing by 2t is going to simplify a little bit. Get this down to just 4, and get this down to 355. The r squared times this is r cubed, and this r squared times this r to the negative 2 clears out my negative exponent, so it goes away completely. So now we simplified, and notice that the thickness doesn't really go into it. We don't really need to know the thickness because it all washes out right here. And then just solve this for r. Add 355, divide by 4 pi, take the cube root. You get about 3.05 centimeters for the radius. And if you plug that back in, our formula for h above was this. Plug that in here, and you get about 12.2 centimeters. And I challenge you to actually get a soda count out and measure it. And I think you'll find that this is pretty darn close. Even though it's not a perfect cylinder, you're going to see that you get really close to a radius of around 3 and a height of around 12 on centimeters. So the amount of aluminum is minimized when the radius is approximately 3.05 centimeters and height is 12.0 centimeters. If you measure a typical soda can, you'll see that it's very close to these dimensions. Over the years, further refinements to the can, including curving the bottom and pulling in the top a little bit, and these refinements to the basic cylindrical shape make the cans easy to stack, make them sturdier, and further minimize the cost of producing the can. Of course, the can has some other restrictions. It's got to be able to be held easily, and it has to have the branding decorations and the information that they print on the sides. So do you think designers of the can know some calculus? You bet they do. And they use it regularly to save the company lots of money on production. Even though this may only save a few cents per can, or even a fraction of a cent, when you start doing millions and millions of cans, then that saves lots of money. Here's another example. A baseball team plays in a stadium that holds 51,000 spectators. With ticket prices at $10, the average attendance has been 38,000. When ticket prices were lowered to $8, the average attendance rose to 42,000. Let's assume the demand function is linear. What is the demand function? Well, the slope then has to be delta Q over delta P if Q is your output variable. So that would be 42,000 minus 38,000 over 8 minus 10 is negative 2,000 spectators per dollar. In other words, for every dollar increase, you lose 2,000 spectators, or for every dollar you lower the price, you gain 2,000 spectators. All right, so the quantity is the slope times P minus P1 plus Q1. That's the point slope formula for a line. 10 goes in here, 38,000 here, slope is there. Distribute and combine like terms to get it in slope y-intercept form. Q is negative 2,000 P plus 58,000. So what's the revenue function? By the way, this is going to have some limits because this stadium will only hold 51,000. What's the revenue function? Well, revenue is price times quantity. So if you have P is the price, the quantity is given by this formula up here, then distribute, we get this quadratic polynomial function, which gives the revenue as a function of the price. What ticket price should be set to maximize revenue? Well, now that we have the revenue as a function of price, just take a derivative. It's quadratic, not too hard to do. We get that. Set it equal to 0. That's linear, not hard to solve that. We get 1450. So to maximize revenue, they should set the price at $14.50 per ticket. At that level, what would they get? If you work that out, it is the quantity is 29,000. That's under the 51,000 that they could do. So you have this trade-off, right? If you charge too much per ticket, then not enough people are going to come. If you charge too little per ticket, a lot of people come, but then you don't get as much per person. The sweet spot for the maximum is $14.50, according to this working out. And we get that. It's a realistic type of problem, except that this might not be a linear function here. All right, one more little section here, and I've got a few more examples for you. Another application of derivatives is called related rate problems. In these problems, we obtain a relationship, an equation, among two or more variables, and then we take the derivative of both sides of the equation in terms of a new variable, usually time, t. We'll be applying the chain rule on both sides, and it's going to leave derivatives of each variable introduced in terms of t, or with respect to t. After taking the derivative, substitute in known values of the variables and the known rates of change, the known derivatives, and solve for the missing derivative. Okay, so I've got a couple of cool examples here. A ball is dropped out of a window 30 meters above the ground. It's dark outside except for a light from a lamppost, which is 2 meters above the ground. The ball is dropped directly above a point that is 5 meters away from the base of the lamppost. How fast is a shadow moving along the ground 2.42 seconds after the ball was dropped? I remember doing a problem like this when I was in Calculus 1. I thought, wow, that's crazy. There's not enough information to solve that problem. And then after I got into it, I realized it wasn't that hard to solve. Calculus is amazing and very powerful. The ball is dropped from a point D in the diagram. Okay, it falls straight down at a constant rate of acceleration due to gravity. Okay, and once it gets below the height of the lamppost, it's going to start giving a shadow. So here's the height of the lamppost down here, and somewhere it's going to get below the height of the lamppost and start casting a shadow out here. So the shadow's out here. Here's the ball, and the light's going to come out here and make a shadow. Now, as this ball falls a little bit more, that shadow's going to come in and move toward this point right here. Okay, so if we orient this so that the lamppost is above the origin at the point 0, 2, the ball is above the point, well, it's x equals 5 all the time, and then the shadow's out here on the x-axis at some x value. Actually, I'm going to let x be this red distance, so it's actually the shadow is at the x value of x plus 5. Okay, but this is going to be x here. And what we want to know is how fast the shadow moving. We want to know what dx over dt is. So let's see what we've got here. Well, we know x over y is the same as x plus 5 over 2. That's from similar triangles there. All right, so cross multiply here. 2x is x plus 5 times y. Let's see, what did I do next? Made this xy plus 5y. And then I subtracted xy from both sides. Factored the x out and got 2 minus y times x equals 5y divided by the 2 minus y. I got x as a function of y here. So I got x in terms of y. Now let's see. Okay, so I have okay, so I took this version right here, okay, and took the derivative of both sides with respect to t. The derivative of 2x is just 2 times dx over dt. Derivative here, I use the product rule. It's x plus 5 times dy over dt plus y times, well, the derivative inside is 1 times dx over dt. I want to find dx over dt, so I need to get it by itself. So I want to take this and subtract y times dx over dt from both sides and factor the dx over dt, so I got 2 minus y times dx over dt. Divide by the 2 minus y, I get dx over dt is x plus 5 over 2 minus y times dy over dt. Now I want to know what happens at a particular time, 2.42 seconds. So I need to plug in what x is, what y is, and what dy over dt is. Okay, so I've got a little computation on the side over here. When we talk about a falling body problem, we know that the acceleration due to gravity is approximately negative 9.8 meters per second square. It's constant. Well, technically it's proportional to the, or it varies inversely as the square of the distances between the object and the centers of the object. But when you talk about an object that's near the surface of the Earth, like a ball, that's going to be pretty much constant, and we can pretty much neglect the effect of the air. Now, if we were dropping a balloon or something or a feather, it would be different. But for a ball, this would probably work. Okay, so then the velocity then is the antiderivative of that. So it's negative 9.8t plus v sub 0. And we just dropped the ball. We didn't throw it up or down. So the v sub 0 is 0. So it's just negative 9.8t. That's meters per second. And that's dy over dt. That's going to be important. Then y is just the antiderivative of that. So it's power goes up to 2, divided by 2, that's negative 4.9t squared plus v sub 0t plus y sub 0, and that's in meters. And the initial height was 30, so that's 30 for y sub 0. V sub 0 is 0, so that middle term goes away. Now, if we plug in a time of 2.42, we can plug in, we can plug in to find the y, the v, the a. Of course, the a is constant. So we can plug it in this formula right here to find the y, and we see that it's approximately 1.30364. So that was the y. That's what I put right there. Okay, so dy over dt is 9.8 times t, and that's negative 23.716. Plug that in for dy over dt. So it was falling down at 23.716 meters per second. And then what else do we need? We need to find the x, right? And the x, that's why I had to solve for x up here. X is 5y over 2 minus y. And we already figured out what y was, so plug that in here, and we get approximately 9.360388305. So I plug that in here. Now it's just arithmetic. Do that in your calculator, and we get dx over dt. X is decreasing at 489 point something meters per second. So that shadow's flying along there, pretty fast rate. All right, here's another related rate problem. A swimming pool is 50 feet long, 20 feet wide. It varies in depth uniformly from 2 feet at the shallow end to 12 feet at the deep end. Suppose we're filling it up the pool at a rate of 1,000 gallons per minute. At what rate is the depth of the water at the deep end increasing when the depth is 6 feet? A gallon is 0.1337 cubic feet approximately. So I've drawn a picture here. It's got a constant width of 20. As long as we're below this this line here where it's 2 feet here from the top of the pool, we're looking at the shape of a triangular prism, a right triangular prism. Y is the depth here. X is going to be the length this way, and the depth, the width here is fixed at 20. So Y and X are both increasing as this thing fills up with water, but the 20 is staying fixed. And we're going to do this at the point 6. Did I work it out at 6? Or did I work it out with? Yeah, I worked it out at 6. Looks like I've got it the picture at 10, but it should be 6 here. So let V be the volume of water, T be the time since the filling began, Y be the depth of water at the deep end, X is the length of water at the surface, and all lengths are measured in feet. T is in minutes, V is in feet per minute, and V is in cubic feet. Volume is 1,000 gallons per 1 minute, and then 1 gallon is 0.1337 cubic feet per minute, so that works out to be 133.7 cubic feet per gallon. So notice X, Y, and V are all changing as T changes. Okay? Now, however, the width remains at constant at 20 feet as T changes. From similar right triangles, we're going to see that, let's see, X over Y, tangent of that angle, is the same thing as 50 over 10. Oh, this 10 is the length here, from top to bottom here. And this point here is at 6. Okay, so 50 over 10 is 5. Solve for X. X equals 5 times Y. So X is always going to be 5 times whatever the Y is. So when this is 6, this will be, when Y is 6, X will be 30. Okay, so, but we don't plug those values in. It's important when you're doing related rate problems, you wait on plugging in until after you've done the derivatives. So the volume is going to be the volume of this thing, which is the area of this triangle times this depth here, or this width here. Well, the area of this is 1/2 the X times the Y, and then the volume then you get by multiplying that by 20. So 1/2 XY times 20, that's 10 XY. But then X is 5 times Y, so that's 50 Y squared for the volume. So now we got the volume in terms of just one variable. That's not nice. So now take the derivative of both sides with respect to t. We get dv over dt is 100y dy over dt. Solving for dy over dt, you get dy over dt is 1 over 100y times dv over dt. When y is 6, you plug that in. Y is 6 here. And dv over dt is 133.7 with the correct units here. Now do this on your calculator, you get 0.22283 with the 3 repeating feet per minute. We could leave it like that or multiply by 12 inches per foot to get about 2.674 inches per minute. So we see that when the depth is 6 feet, the deep end is increasing at a rate of 0.2238 feet per minute or 2.674 inches per minute. All right, one more. An airplane flying east at 400 miles per hour goes over a certain city, certain town at 11:30 a.m. and a second plane flying northeast, that is north 45 degrees east, at 500 miles per hour goes over the same town at noon. So we'll be explicit, north 45 degrees east at 500 miles an hour goes over the same town at noon. How fast are they separating at 1 p.m.? So we're going to look at a diagram, and we're looking down at the planes from directly above. Here's the town over here, 45 degrees. It's actually 45 degrees from north, so it's actually 45 degrees this way. But that's also 45 degrees this way, which is pi over 4. And this plane is traveling at, let's see, how we got it? Let's see, look here. This plane is traveling at 500 miles per hour, and from noon to 1, it's traveled 1 hour, so it's actually traveled 500 miles. The other plane, so this is the position of plane 2 at the time we're talking about, at 1 o'clock. The other plane has got an extra half an hour. It was flying, so it flew an hour and a half at 400 miles per hour. So that is 600 miles, and that's going to be just due east of the town, out here. So 600 miles. So that's actually drawn to scale. And so we want to know how fast this distance C is increasing. So we need a relationship among these sides A, B, and C. Well, there's a nice little relationship among the sides of any triangle, not just right triangles, but any triangle, called the law of cosines. It's actually a generalization of the Pythagorean theorem. And you can see my videos for more details about that on trigonometry, so see how that's derived and how it's used in some problems. But let's use it here. The law of cosines says c squared equals a squared plus b squared. That's the Pythagorean theorem. Minus this correction term, minus 2ab cosine of angle c. Angle C is the one across here. Okay, where A, B, and C are the lengths of the sides. So remember, A, B, and C are not fixed. They're all changing. The only thing that's fixed here is this angle at pi over 4. So that angle is fixed, so I can plug that in. Cosine of pi over 4 is square root of 2 over 2. Twice that would be just square root of 2. So that square root of 2 represents 2 times the cosine of the angle C. So now we have a relationship here among three variables, A, B, and C. Take the derivative of both sides with respect to t, and I get 2c dc over dt plus 2a dA over dt plus 2b dB over dt, and then I have to do the product rule here. Minus square root of 2a times derivative of b with respect to t, and then plus b times the derivative of negative square root of 2a, which is negative square root of 2, and then dA over dt. So we get that. Don't forget the chain rule going on here, all over the place. Now what we're looking for is dc over dt, which we can solve by just dividing both sides by 2c. And so there we have our expression. Here it is. C then is the square root of a squared plus b squared minus the square root of 2ab, just solving this for c by taking the square root. So now there's our expression. We just plug in everything. A is 600, which goes here and here, here and there. dA over dt is 400. That's how fast plane A is flying. That's here and here. And similarly for the other things. Just plug in all the stuff where it goes. Just be careful that you get all things in the right places, right? dA over dt is how fast plane 1 is flying. dB over dt is how fast plane 2 is flying. And now we actually plug in the actual values at the of A and B that we know, and since I got everything in terms of A and B, we can just plug that in, work it out, and it turns out to be about 238.6, 239 miles per hour. Okay. Well, that's a quick sprint through differential calculus from Calculus 1. We touched on most of the main ideas and skills here, but we certainly did not cover everything, nor did we get a chance to develop ideas slowly and carefully. The next step for you would be to go back to the review sections of the notes for Calculus 1, Units 1, 2, and 4, and 6, and work or rework the problems there and check them against the provided solutions. If you don't have my notes and you're just watching these videos, then I'm going to follow this up in this playlist by reposting the videos from those reviews, and be sure to stop the video and work the problems of shells before you check them. After you get through that, you'll have a pretty good review of the differential calculus part of Calculus 1. If you're in my Calculus 2 class and you're using this to help you review, then the next step for you after that would be to start working on the homework set 1 problems online. And then after that, we'll come back and do something similar for the integral calculus portion of Calculus 1 later in this playlist. Okay, there we go. That's differential calculus in about 83 minutes.